Now in my second video I'm going to show you what is an ideal transformer, what for us is an ideal transformer, and I'm gonna explain all these equations. So if you watch my previous video, in the introduction I said that you need to know a chapter called magnetic circuits. I did that already. Check out my description to see that playlist if you haven't conquered that lecture. So you need to know the magnetic circuits. So yeah, in my last video I just said some basic stuff about transformers. Now I'm gonna go in some heavy detail. Now here we have a transformer, and here is the core of the the transformer. This is a magnetic circuit. It has a winding with number of turns N1, and it has a secondary winding with number of turns N2. In the secondary, we have connected to these terminals a load, but we have a switch. So in the first situation, we're gonna have an open switch. That's the situation where there is not going to be any current in the secondary. And here we have energy source V1 that we are going to provide on this winding. And where in the winding when we are putting the energy, this is called the primary, and the energy where it is going out, and that is called the secondary. Now first we are going to see what are the characteristics of an ideal transformer. So we have three characteristics of ideal transformer. Now the first characteristic is that the winding resistances are negligible. So this has a resistance of 0, and also this one has resistance of 0. You know that every conductors have some resistance, but in an ideal situation, for an ideal transformer, it is negligible. Now, second, all fluxes are confined to the core and link both windings. That is, no leakage fluxes are present, core losses are assumed to be 0. So we don't have any fluxes that are going to go outside. We don't have any leakage fluxes. So so the flux that we produce by giving the source on the primary is all confined in the core. So the same amount of flux goes through this winding over here, and the same amount of flux goes to the winding over here. In reality, that is almost correct. In reality, in good transformers, we have really small flux leakages. So yeah, the same amount of flux goes here, and here there are no flux leakages here in an ideal transformer. Now the third characteristic, and the last one, is that the permeability of this core is infinite. So mu goes to infinity. And when you have a magnetic core that has infinity permeability, then you don't need, therefore, the exciting current required to establish the flux in the core is negligible. It's so small that is negligible, almost 0. So you only need sinusoidal voltage for a sinusoidal magnetic flux in the core. I explained that. If you don't know what is exciting current, I explained it in my lectures of magnetic circuits. So you need to know that. And that is the net MMF required to establish a flux in the core is 0. So net MMF Ni that is equal to 0. In real life that isn't the case, but we can assume that the net MMF for a infinity permeability of this core is 0. Okay, now let's take the first situation where this switch is open. So there is not going to be any current. And this current I1 is not the exciting current, that is not the current that is establishing flux. It is a current that is going to this is the current for the balancing of this net MMF when this is closed. But first now we say that this switch is open, so and there is no current here, neither here, because the current there is no exciting current, so we only have voltage that produces this MMF. So the induced voltage on this winding, which is the primary, because the winding resistance is negligible, E1 is equal to V1. V1 is the voltage that we supply to the primary side of the transformer, and that is equal by Faraday's law. You're not taking the minus sign, we're just taking that this is a scalar, is equal to the flux linkage N1 times the change in magnetic flux. So that is why with DC we can't we can't establish the change in magnetic flux. With direct current we only have steady flux. So the change in the flux is what we need to induce the voltage on these windings. So V1 is equal to E1, which is equal to the Faraday's law, N1 times dF by dt. Now, V2, the voltage on the terminals of the secondary, is going to be equal to the induced voltage of this winding here, and that is equal to N2 times dφ by d flux by dt. So you know that the same amount go in the ideal transformer, all fluxes are confined to the core. So this flux here is equal to the flux here, and the relationship between V1 and V2 is here. So when you divide V1 by V2, these two cancel each other out, and then you have N1 divided by N2, which is equal to this small letter A, and this is called a turns ratio. So what does this mean? This means that, for example, V2, looking at this equation, is equal to V1 times N2, number of the turns on the secondary, divided by number of turns of the primary. Now, as you can, V2. Looking at this equation, you can see that the voltage is directly proportional to the number of windings on the secondary times the supply voltage on the primary divided by the number of turns on the primary. Now, as you can see, if you have more turns on the secondary than on the primary, you will have a higher voltage. If you have smaller number of turns on this secondary than on the primary, you will have a smaller voltage on the terminals. And this N1 and divided by N2 is called the turns ratio. That is very, very important in transformers, and in real and transformers this is pretty much the same formula. So this is a very, very important formula, and this A is called the turns ratio. All transformer manufacturers provide this on the small tables on the transformer. Now, I hope you know that if you have more number of turns on the secondary, more the voltage. If you have smaller amount the number of turns on the secondary, then on the primary, smaller the voltage, looking at this equation. Okay, so that is for the voltages. And what about the currents? Now, a second situation is when this switch is closed and we have a load, impedance of the load. We connected a load on the secondary. So if you have a voltage and you have a load and you have a closed circuit, then the current will flow in the secondary. Because this current here, and we have number of turns N2, provides an MMF, then this source here is gonna draw a current that is equal to I1, so the net of this ideal net MMF of this transformer is equal to 0. If that was not the case, if this wouldn't, if this here would not draw the current, if it was just like this, then this I2 current would provide another magnetic flux in the core, and this here would be unbalanced. So V1, E1 here would not stay the same. So that's why when this switch is closed, then you have a primary current I1 on the primary side when this here secondary draws a current. Now, because the net MMF of this magnetic core must be 0, N1 times I1 and minus N2 times I2 is equal to 0. This also by Lenz's law, if the magnetic flux is going in this direction, the I2 must provide opposing magnetic flux in this direction, so that the current will go in this direction, right here. So N1 times I1 minus N2 times I2 must be equal to 0, and that is the net MMF for the ideal transformer. Because real transformers draw some exciting current, this is not 100% correct for the real transformers, but also it stands, this formula also stands for the transformer, because the exciting current is very small in relationship with the I1 primary current. So when we have a load here and when we draw a current, then here comes the current I1. So this is another situation when the switch is closed. So looking at this equation, when we minus N2 times I2 transfer to the other side, this becomes plus, and then you have that I1 is equal to N2 times I2. And the relationship I2 divided by I2, so if you transfer I2 to this side, you have I1 divided by I2. So the here relationship is not equal to N1 divided by N2. It is equal to N2, and when we transfer N1 to the other side, we have N2 divided by N1. And this is N1 divided by N2 is A, and this is just opposite situation. This is 1 divided by A. So now, as you can see, if we have, let me just rearrange this. I2 is equal to I1 times N1 divided by N2. Now, as you can see here, if we have more windings over here on the secondary than on the primary, then the voltage will be increased, yes, but the current will be decreased. Looking at this equation, that is very important to know, because in my last video I showed you how the electrical energy is transmitted through power lines in some countries, and you saw that there was an electrical generator that produced 30 kilovolts of voltage, and the first stage was stepping up the voltage. So because the the transmission lines are very, very long. So longer the lines, the bigger the resistance of those lines. And if you have a high current that goes through those lines, then the power losses on those lines are very, very high. And that's why Edison lost to Tesla, because Edison couldn't, with direct DC generators, maintain that problem. But Tesla stepped out the voltage very high and lowered the current on the transmission lines. That's why on the first stage you have high stepping up the current, and then I2 squared R is smaller, so the joules losses are smaller if you have a smaller current. And now if you have a smaller amount of the number of turns on the secondary than on the primary, then you have a smaller voltage, but the current increases. Also, it depends on the load. The impedance of the load is also very important, but let's say that this is 1 ohm. If you have a higher number of turns here, the smaller number of turns than on the primary, the voltage will decrease, but the current will increase. Okay, so now I know that you understand this turns ratio and how we are stepping up and stepping down the voltage. And now, then we have another equation, which is very important, that the power input V1 I1, this is the power input, is equal to the power output. In an ideal transformer, there are no power losses, so the efficiency, the power efficiency is 100%. Also from this equation you get that V1 divided by V2 is equal to I2 divided by I1. So the higher the V2, the smaller the I2. The higher voltage on the secondary, the smaller current on the secondary. Smaller voltage on the secondary, higher current on the secondary. Okay, and this is just the RMS values, and it stays the same. The RMS V1 is equal, divided by V2 is also the same as this current voltages, how you say it, N1 divided by N2, and RMS of the current is the opposite. I1 divided by N2 is N2 divided by N1, which is equal to 1 divided by A. Also, this is the same as here, just these are the RMS values. So the RMS values are with the same equations. Now I hope you learned what are the equations and the transformer, and I know now I'm going to show you what is an impedance transfer. I'm gonna do an example. and then gonna show you the polarity, and then polarity of the transformers, which is very important, and then I'm going to show you what is a practical transformer and what is the equivalent circuit of those practical transformers in real life. So thank you for watching, and see you in my next video.